Hi, this is Crossdot and Nabla, and in today's video, we're going to be starting over Chapter 13, Integration of Multiple Variables. And personally, this is probably one of my favorite topics, not only in Calculus 3, but in all of math, because personally, I think expanding our ideas of understanding what integration is beyond two variables is beyond just a single variable integration is very, very interesting. Like, what does that mean for things like center of mass? The Jacobian we're going to cover later on in this chapter. What do these regions even look like? How do you even solve for them? And again, it's like a very mechanical process that once you learn, you will never forget. And it's one of those things that's just really, really cool to solve. But of course, we have to start off with the basics, and we're going over double integrals over rectangular regions, which is the most basic of them all, because in essence, we're thinking kind of like in terms of single variable calculus, where we integrated like this. We go from, let's use y instead. We go from a to b of f of x dx, usually, equals the area under a curve. However, in this case, if we're doing a double integral, instead of getting an area, what would one assume we would get instead? Would it still be area? Would it be some other quantity? Well, in fact, we would get a volume, right? So if we look right here, for example, this green right here is a 3D shape that we're mapping on, right? And this white box right here represents a rectangular region carved up within this function, right? And from there, you can solve for your volume within this region, right? That's pretty cool to know. And let's just start off with a really, really basic example, right? We have if f of xy equals this piecewise function, right? We have this piecewise function right here, and we're trying to solve for the value of it. We can do a couple of things. First off, we can actually just draw out some coordinate planes like this. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, like this, right? What we can do is we can just carve out little rectangles in our area, right? So we have 1 right here to 4. We're going to make this first one red, right? And then we're going to go from 0 to 1 like this. So that's region 1. And region 2 is like this. So it's the same x values, but we're going up by 1 for the y, right? And in that sense, what we're really doing here, this is the most fundamental basic example of this, right? We're just getting boxes, right? We're getting these big boxes because these values are all constant. These values aren't changing with respect to any coordinate direction, right? Right here, our value is going to be -1. So we can actually use it's going to go into the page like this. In physics, for magnetism, you would usually use that. And then for this is +2, and it's going out of the page, coming right at you, right? Use your right hand rule, points out at you, right? And in essence, what we can do now is we can just say we have our horizontal, we have our y direction and x direction being constant value. So we have 3 times 1, which is 3, times 2, which is 6. So 3, so we have region 2 slash R2 equaling 3 times 2 times 1. We have region 1 slash R1 equaling, again, 3 times 1 times -1. And in this case, we would get equal to 6 equal to -3. 6 minus 3 is 3, and that's our volume across this region, right? And that's the most fundamental basic version of it, right? If we recall back to single variable calculus, we remember one of the nice things that we have to approximate a function, right? So let's just draw out our curve, some arbitrary curve, right? We can use Riemann sums to approximate the area. And the more boxes that we have, the more accurate our result's going to be, right? And in essence, that's what we're doing in multivariable calculus, but instead of having rectangles, we're having actual 3D boxes that extend up into the third dimension as well, our z, right? And to actually define it, we have the definition of the double integral right here. We have z equal to f of xy, just explicitly defined f of xy is a function of multiple variables defined in a closed rectangle R. So the limit as p approaches 0. This is just a summation thing that we learned in Calc 1 to define what a limit is, to define these Riemann sums or these Riemann boxes. Now we can say approaching the actual function itself, approximating the area, or in this case, the volume underneath this function, right? And like what we did in Calc 1, where we said that the limit would approach this integral, it's the same idea for our multivariable function, right? And if we look at this image right here, right, we can see one of the nice things is that this rectangle right here, they're all equally spaced out, right? The idea is, though, is that your delta x or delta y will become your dx dy because it is so infinitesimally small. Remember how we said in Calc 1, our delta x is going to become infinitesimally small, approaching 0, but it'll never hit 0. It's essentially 0, right? That's what we're getting at right here. These boxes are going to become so tiny that they actually encapsulate the entire volume underneath the region. It's not the area, it's the volume, because we're taking in multiple variables now, right? And we can see right here, the smaller and smaller you get, say like we used like 4 of these, right? We would get a wholly different interpretation of the value, right? And again, that's in essence why these smaller approximations are so valuable for calculus and math in general. Math oftentimes helps us approximate and actually solve for these types of problems, right? And we look at this, we see dA. And we might have seen dA before in Calc 2 if we were talking about polars, usually, which we're not getting into polars in this video. That's going to be in section 13.3. But in this case, we would say that something like a polar would be equal to the area equals 1/2 r squared d theta. This is just also your dA, but it's a different type of dA as opposed to this, right? But if we're talking about rectangular regions, our dA just refers to dx dy, right? And then this is where the delta A comes in, because the delta A represents the delta x times the delta y. And if we know that dx dy equals delta x, delta y, the limit approaches 0 for both of those, right? Then we can say that dA, you write dA like this because it's a big A, is equal to dx dy. And then for the integrability theorem, I don't know how you would say that, but essentially the ability to integrate a multivariable function across a rectangular region. If it's continuous, then you can integrate it. That's something very straightforward we learned from Calc 1. A lot of the continuity rules, as we've seen with like limits and partial derivatives, they still apply to multivariable functions from Calc 1. We're just extending them. We're extending the ideas of what these topics mean in broader context, right? Example 2, I'm not going to cover this in this video because I feel like it's kind of a exercise that is trivial for those who already understand the process of integration in single variables, because if you're watching this video, it's assumed that you would have already taken Calculus 1 and Calculus 2. You would know the process of how to like approximate these integrals with Riemann sums, right? Or now with Riemann boxes, right? And in fact, we're just going to go down to the next example right here. We have iterated integrals, where we have, again, the total volume is the sum of many rectangular boxes, and we take the number of boxes goes to infinity. The same idea with the rectangles 2D. And we can also just do this trick of just taking these infinitesimal slabs of delta y to get a of y dy, right? And then we can get our value as well from there. Again, this trick right here, this is fundamentally saying the same thing as just saying a to b, c to d of f of x, y, dy, actually dx, dy. And the reason why is because it's a rectangle. You can switch the boundaries, right? It doesn't matter if you are going from here to here. What matters is that you are summating the entire rectangle, right? There are some regions, for example, like a triangle. If you were trying to integrate a multivariable function over a triangle, that's where your order of integration actually matters, right? So say like we're at x equals 0 to x equals 1, we're at y equals 1, right? And we want to integrate some function over this area, some function over this area, right, to get its volume. So what we can do is we can do like this. And we know that our y is always going to be bounded by y equals x. So it's going to be from 0 to y, and then from 0 to 1 of some f of x, y, dx, dy, right? And that's how we get the result. But we're going to cover these types of problems more generally in section 13.2. It was just like an introduction to that. So when you have these rectangular regions, again, you can flip the order of it, of the order of integration. But in non-rectangular regions, like in a triangle or a circle or any other non-rectangular shape, you cannot change the order of integration just by flipping them. You have to actually rearrange the bounds, right? And then some other properties, we know that integration is a linear operator. And what that means is that you can add it up and you can summate different regions together to get the volume, right? So like, for example, if we have k of f of x dx over some region r, actually over some a to b, let me actually move this so it's more salient for you, the viewer, to understand. This just equals k f of x dy, f of x dx a to b. We know that the summation of this, we have two functions over the same region. You can split them apart, save some time. You can actually add regions, and it's kind of like saying that we have some f of x dx from a to c equals integral a to b f of x dx plus integral of b to c f of x dx. You can just add up these and you can get your whole region. For statement C, this one seems kind of straightforward. If you're integrating over the same region and you know that for the entire region that g of x is going to be greater than f of xy, then you know that the integral is also going to be greater, right? And for rectangular regions, if you have r times some constant, you can just do k times the area of the region r, right? Because you're only just integrating with respect to the constant, right? It would just be the area of the region, right? So it would be just k times r. To actually get into some examples, we can work through them right here. Try this on your own and feel free to pause the video. I would recommend writing out your integral first and actually solving step by step, because one of the big problems with getting to higher level math is the ability of losing like the very easy steps of solving these types of problems, right? Even though this problem does relatively seem straightforward, and it is, it's still imperative that you should write down every single step, because it's important to develop the processes by which you would solve these more complicated integrals that aren't just rectangular regions, right? And all right, let's get right into it. So let's see, we have 0, we have 0 to 2, 0 to 1 of 7 minus y dx dy. And then I'm going to do this. And also, one thing you can also do is you can sketch this because it would be a cylinder as well. Not like the traditional geometry definition, but the definition where you extend it out infinitely into different planes. And we can actually show that example. We can show it after we finish this, right? The actual integration, but we would get 7x minus xy evaluated from 0 to 2. And then you would get 14 minus 2y minus 0. So then you would get this, right? And then you would get 0 to 1, 14 minus 2y dy. And this is just a very straightforward integration, 14 minus y squared. Which we would get to be 14y minus y squared. 0 to 2, we would get 14 times 2 minus, oh no, it'd be 14 times 1. Oops, that's, again, it's always important to check your bounds. That's a very glaring mistake that I very easily could have made. You get 13 units squared, which we did the calculus way, but we can also do the geometrical way as well, which I will show. And for very basic regions like this, you can actually use this. So let's just draw this out. And then we have our little box within 0 to 1, 0 to 2. So let's just label out our xy coordinates. X, Y. Okay. Let's just draw out this box. Let's actually use blue instead. I feel like blue would be a more striking color. And then we should get it like this. Right? And we would get this box, right? And in fact, you could actually just solve for it like a trapezoid, where you would get your different values corresponding to your different x and y, right? So in this case, you would see that the base is just 2 units, and then your heights correspond to different values, right? So it would be at y equals 0, it would be 7. So we have height 1 equals 7, height 2, oopsie, oh my gosh. Height 2 equals 6. And then you would do 7 plus 6 over 2 times 2. And you would get 7 plus 6 equals 13 units squared. And again, that's a really basic example, but you can also use geometry like you did in Calculus 1 to solve some very basic integrals like this, right? But now let's get to some more difficult problems relative to the topic itself. If you want to try this on your own, feel free to pause the video, and let's get right into it. All right, so we're integrating with respect to x, so let's just take the antiderivative. We got negative 1 to 2, which means we're going to get 2 cubed over 3 minus 6 minus 3 times 2 times y minus negative 1 cubed over 3 minus 3 minus 1 y. So then we're going to get 8 over 3 minus 6y plus 1 over 3 plus which is going to become 3y minus 3y. And then we're going to get 3 minus 9y. So then we're going to get 3 minus 9y, 0 to 4 dy, and then we would integrate this again. We're going to get 3y minus 9y squared over 2, evaluated from 0 to 4. And then the value that we would get from this would be 12. Let's just actually write it out like this. 3 times 4 minus 9 squared. Not 9 squared. 9. Jeez Louise, what's happening with me today? 9 times 4 squared divided by 2. And then this would become 12 minus 72 equals negative 60 as our final result. And if you want to, as an additional exercise for this video, you can try and integrate in the opposite direction. You can do dy dx, right? Example 5, let's try this. Let's try this integration, right? So we have this, and I see we can probably do a u sub. And remember, when we're integrating with respect to x, just like we were differentiating, just like we were taking the partials with respect to x, oh my gosh, just like we were taking the partials with respect to x, we're treating y as a constant with respect to x, that different variable, right? And I'm seeing something right here. If you took the derivative of this function with respect to x to get the antiderivative, I feel like you can do something with that. So let's try something real quick. So we can try x plus, we can try it to be like u equals xy plus 1 du equals y dx. Okay, I see something right here. So this is replaced with our du, and this is replaced with u squared. This makes our integration a lot easier. So like to actually rewrite this down here, given our new information, I'll actually keep on writing in red. So we have this, which is going to become du dy all over u squared. And let's keep the u squared, let's keep the dy elsewhere for now. And if we're integrating from 0 to 1, we have to replace 0 with x, and 1 with x, and the u, right, the substitute. That's how we do the u sub, right? So if we do 0 into here, we would get x being 0, 0 times y, 0 plus 1 is 1. And then 1, we get x equals 1, 1 times y is y plus 1. And then we get 0 to 1 still over here. Perfect. Now we can rewrite this to integrate it. We get u to the negative 2. We get 1 y plus 1, 0 to 1 du dy. And then you would get the reverse power rule, which we know, which is just going to be u to the negative 1 over negative 1 from 1 to y plus 1. So then we're going to get negative 1 over y plus 1 plus 1 to get our new integral from 0 to 1 dy. Right? And now we can do our properties of integration again. And we know that this is going to be a natural log, y plus 1 plus y evaluated from 0 to 1. So then we would get negative ln 2. And I should probably clarify this right here. This is supposed to be an absolute value, not an extra 1 attached. Negative ln 2 plus 1 minus ln minus minus ln, so plus plus. And then we're going to get ln of 1, which we know to be 0, 0, plus 0. So this all goes away. And we're going to get negative ln 2 plus 1, or 1 minus ln 2, which is about like 0.306. Some value approximating that, right? And then we have example 6, and then we have our last example, example 7, which we'll cover. We have this right here. We have example 6 covering this entire region. If you want to try this example on your own, feel free to pause the video, and let's get right into it. So let's see. I think the easiest thing to do first is I could do a u sub immediately, because 1 plus x squared equals u can very easily become 2x dx equals du. And I feel like that would actually be easier for us to do. So let's just do that instead. So let's just write out our values first. 0 to root 3, 1 to 2 of x, y, 1 plus x squared dx dy. And let's say that u equals 1 plus x squared du equals 2x dx. And then u of 0 equals 1, u of root 3 equals 4. And now we can rewrite our order of integration. So we can do this. We can rewrite this as x, y, root u. And then we're going to get du over 2x dy from 1 to 4, 1 to 2. And then we're going to see this cancels and this cancels. Well, just the x actually cancels, but it's all good. And then we're going to bring out the 1/2 to the front. And then you're going to get y root u du dy. And in this case, we're just going to keep the y as a constant, actually. So we'll just bring it out to the front, like with this. And then this will just become y over 2 like this. Now we can do our reverse power rule. We know that this is u to the 1/2. So we're going to get 2 over 3. We're going to get plus 1 divided by 1 over 2 plus 1. So we're going to get 3/2, we're going to get 2/3 for our u, right? Yeah. So we're going to get u to the 3/2 times 1/3. Wait, hold on. Just to recall, right? We have x to the n. You integrate this, you get x to the n plus 1 over n plus 1. Yeah, okay. Divide that by 3/2, which will move to the side, right? Divide this from 1 to 4, we get 8 minus 1, that's 7. 7 times 1/3 is going to be 7/3, because it's going to be, yes, it's going to be 7/3 here. And then we're going to get 1, 2, 2 of y times 7/3 dy. And this is going to become y squared over 2, evaluated from 1 to 4. So this is going to become 7 minus, not 7, it's going to become 8 minus 1 half, which is equal to 7 halves. No, it's going to become 15 halves. What am I doing today? Jeez Louise. And then our result would be our result would be 15 over 2. Did I make a mistake over here when I was doing my differentiation? 2 over 3 is 1 over 3. 7 over 3 times 15 over 2. Let me double check actually. So when we got to here, we had 1/2. And then we got 2/3. So that's 1/3. Like that. So we got 7/3 from there. So am I supposed to get, oh, I recognize my mistake. Again, this is a silly mistake that I just made. And this is actually a great reminder to always check what you are doing, because, oh my gosh, that was actually freaking me out because I thought I was doing something wrong. Again, this is a great reminder in this video, even alone, to always check your bounds when you're integrating, because I just completely blanked on that for a second. I didn't realize what I was doing there. So now we get this. Now we can multiply these two because they're both constants. We got 7 over 3 times 3 over 2. This cancels out, so you get 7 over 2 as your final answer. How awesome, yeah. And that took me about a couple minutes to solve, and I've been doing this for an entire year. So as a reminder, this is a good example in this video alone to just check your bounds when you're integrating. Always be careful with your problem solving. And then our last example, we want to find the volume enclosed in the first octant by z equals 4 minus x squared and y equals 2. So if you want to try this example on your own, feel free to do so. Let's get right into it. Okay, so it's going to be x, y, z. Let's just mark this off in green. 1, 2. And then we're going to get red as our graph. And whenever we have it in the first octant, we want it to be when x, y, and z are greater than 0, right? So I already have like a general sketch of what this double integral would look like. So it's going to be from 0 to 2, 0 to 2, because we know that the minimum y can be a 0, so I mean the first octant, and then our x can only be from 0 to 2, because right here, this is when x equals 0. That's our max, right? Down here is when x equals 2, and that's going to be our minimum when it's going to be in the first octant, right? So that's how I would have deduced it. dy dx, and you can go either way. And I think we're just going to do dy first, because that's just pretty straightforward. So then we're going to get y times 4 minus x squared, evaluated from 0 to 2. This is going to become 2, 0 to 2, 4 minus x squared dx. And the reason why I just did that shortcut, because this whole thing subtracted by 0 is just 0, right? 0 times 4 minus x squared is just 0, right? And those are some good calculus shortcuts that you can use if you actually know what you're doing, which I, in this video, have not been showing my best effort, but it's all good. And then we can do the reverse integration right here. We get 0 to 2. We get 4 times 2 minus 2 cubed over 3. We get 8 over 8/3, which is going to be 24 over 3 minus 8 over 3, which is 16 over 3. And then we can get our final result of 16 over 3 times 2 equals 32 over 3. And just to double check my notes from A4, I also got 32 over 3. And that is pretty much it, covering over double integration in rectangular regions. Thank you so much for watching, and I hope you guys have a great day.